All right, folks, this is another example of a balanced torque problem, aka static equilibrium. In this particular system, you have three hanging masses, M1, M2, and M3, and M3 is unknown, which is what's being asked of you. And the meter stick in this particular case does have a mass, so we do have to be careful to make sure we include the weight of the meter stick. Otherwise, your answer will come off incorrect. Okay, so here we go. In order for a system to stay balanced, your net torque must equal to zero, which imply that the torque counterclockwise must equal to the torque clockwise in terms of magnitude. While they're in opposite directions, they have to equal in magnitude in order to keep the system stationary. Okay, and then so in my second statement, I just literally set up the magnitude of each directions equal to each other. So torque in a counterclockwise direction must equal to the torque in the clockwise direction, as indicated in the second line there. And then for any of you folks who are struggling with your directions, whether it's clockwise or counterclockwise, the diagram there should help you out. So hopefully you keep up with the rotations of the meter stick. All right. So the first force that you should, I'm just going to take it from left to right, M1, because there is an M1. There must be an F of G to the M1, and that's drawn using that red arrow there as pointing down the page. And then the next thing we have to look at is for the lever arm. And again, the lever arm is measured from pivot to where the force is being applied. In this case, M1 is a distance of 70 centimeters away from the pivot, which I indicated R1 there. Again, I color coded for you so that it's easy for you to follow. And then from there, we can just draw F of G2. And F of G2 I drew just a little smaller, just kind of trying my best to try to draw out the scale. And there's F of G2. And then you need to identify the lever arm for F of G2, measure from the pivot to where the force is being applied. The orange line there, it's indicated by R2. And everything here is perpendicular already for you. So as you can see here, R2 and F of G2 is perpendicular. R1 and F of G1 is perpendicular. So the next thing we have to identify is where to place the F of G for the meter stick. And F of G for the meter stick should always be placed at the center of mass of the meter stick. In this case, it is a meter stick, so the midpoint would be 50 centimeters. So F of G for the meter stick, drawn in green there, must be placed at the center of mass of the meter stick, which is 50 centimeters. And that is indicated by using the subscript F of G stick. And then you need to, again, identify the lever arm for that force from the pivot. So from the pivot, that distance there is a distance R stick. Or in this case, it is 20 centimeters if you measure from here to there, because each one ticks here, and the meter stick is indicated with a increment of 10. All right, and then the next thing you need to identify is the counter torque. In this case, M3 will cause the system to want to rotate clockwise, while everything on the left of the fulcrum will want to cause it to rotate counterclockwise. So M3 there, I drew using the blue vector, and that's F of G3. And F of G3, I know it definitely has to be bigger than the other arrows on the left side, because you do need that weight to counterbalance the rest of the left side. So it needs to be bigger. And then the lever arm, measure from the pivot to where the force is being applied. In this case, I will call it R3, just keep the subscripts consistent there. But R3 in this case is 30 centimeters measured from the pivot to where the force is being applied. And again, everything is already perpendicular in this particular problem. So if you set it up where you have torque by definition is the force times the lever arm. So F of G1 times R1 plus F of G2 times R2, FG stick, and then times R stick. FG stick is right there, placed at the center of mass, and an R stick measured from the pivot to where the F of G is being applied is there. On the right side, you have F of G3, R3 is indicated there. Okay, so the system must be balanced, so the statement must be true. So really from there, all you have to do is plug in all your unknowns from the statement in the problem. And a lot of stuff is given to you already. So you can expand f of g1 into m1g. R1 stays the same. Likewise for f of g2, that can be expanded to mg2. And then here's R2 I carry down. F of G stick can be substituted for M stick times G due to gravity, R stick, and F of G3, R3, M3, G, R3. You notice here though, in every single of these terms, there is a G, the acceleration due to gravity. So we can go ahead and cancel that out because since it appears in every term, we can go ahead and cancel that out in this line here. So I did nothing fancy except for replace M1 with 80 grams as stated in the statement up here or in the diagram. And then the distance R1 is a 70 meter because 40 plus 30 here is 70 centimeters. And then F of G 2 is M2G. But again, the G already cancel out. So all I have to do is use the mass down here, which is 30 grams. G here stands for grams, not acceleration due to gravity. R2 measure from the pivot, from the fulcrum all the way to where M2 is, according to the diagram, that is 40 centimeters, which is there. And then the mass of the meter stick is given in the statement is 150 grams, 150 gram here. Again, acceleration due to gravity is canceled out. And then the distance from the pivot to where the force is being applied for the weight of the meter stick, drawn from the center of mass there, is 20 centimeters according to the diagram. M3 is left as unknown because that's what we're trying to look for. And the level arm for FG3 away from the fulcrum, aka the pivot, is 30 centimeters as indicated in the diagram. So from here, you notice that everything is already given. The only thing missing is M3. So we can just do some calculator work. 80 times 70 gives you 5,600, 30 times 40 gives you 1,200, and then 150 times 20 gives you 3,000. And then I just kind of switch the 30 in the front. I like to keep my variables to the right of the coefficient. You don't have to, but that's just something I do. Other than that, sum everything up on the left side, that comes out to be 9,800, which is equal to 30 M3. And then we divide both sides by 30. You're going to get that the answer is 326.7 grams. And then the unit here, I just kept in grams because the problem has it in grams. So everything here that I'm pointing to with my cursor, that's 80 grams. That's 30 grams, 150 grams. So the unit for here for mass is just grams. So if you're asked to convert it to kilograms, that's the basic conversion that you can do. Okay. I hope this helps a lot. I hope this helps a little bit. All right. Don't be wired. Stay nerdy.